Okay, thanks very much. So yeah, this is about fast rates and linearly solvable Markov decision processes. So this linearly solvable Markov decision processes, they're sort of a strange object for COLT. So
to start it on. Just break in.
Maybe somebody with a better dexterity can come with me.
Okay, you take this.
Yeah, okay, then better take that one. All right, sorry about that. Okay, so what is a Markov decision process in the first place, and what makes it linearly solvable? Okay, I'm just going to start with a very quick review. So this is just trying to describe a Markov decision process, which is about controlling a sequence of states. It's about controlling a dynamical system in a way. So you want to generate a sequence of states in a way that you're trying to minimize some state cost. So what is specific about this about linearly solvable MDPs is that there is a passive dynamics present. So there is some law according to which the system wants to behave. So there's this passive dynamics P. So for example, there's this robot guy that just wants to move around uniformly in the state space. He just wants to walk around, but then you tell them that, okay, there is some cost, there is some threat on the right-hand side, so you want to run away from that, but you cannot go too far away from the passive dynamics. So trying to control the system in a way that you're not too far, but you're trying to minimize cost as well. So formally, this is what I call a linear solvable Markov decision process. So this is a repeated interaction scheme between a learner and an environment. So this is still just the offline version. That's a traditional LMDP framework. So here, well, the learner will just observe the state of the environment, and it is going to pick the distribution of the next state. So it can pick whatever distribution it likes, as long as it is consistent with the passive dynamics to an extent. So after having picked this distribution, the learner is going to suffer loss, which is composed of two components. So one of this is the state cost. So like, how much does it cost for me to be in state xt? And for the control, for exercising extreme controls, the learner has to pay the relative entropy between the proposed distribution and the passive dynamics. Okay, so this is a smooth control cost that the learner has to pay for changing the control. And then the environment is actually going to generate the next state from the chosen distribution. So this is it. And then the goal is to come up with a sequence of controls Q that are going to minimize the average cost per stage. So if I just fix a policy Q, for example, run it for a very long time, I take the average, I observe the losses, and this is what I'm going to try to maximize, or minimize the average loss per round. Okay, so why is this called linearly solvable? Well, this is just one slide to explain that. I really don't want to explain this in too much detail. The story is that you only have to solve an eigenvalue problem in order to compute the optimal control. So this is just some matrix. You just have to find the top eigenvalue of that. So this is why it's called that. So and this is a nice thing because usually for finding the optimal control for general Markov decision processes, you have to solve something much more complicated, like the Bellman optimality equations, and you have to do complicated value iteration updates. Here, no, it's just a linear system. Okay, so it has been well known that there is this computational advantage to studying these processes, but learning-wise, not much has been done. I'm going to review what has been done. So this was the setting that we are looking at so far, okay. Where you had a fixed state cost. And now we're looking at the online setting. This is a sort of more COLT-y setting where you have a sequence of state costs instead of just a fixed one. So these state costs are going to change between each round arbitrarily, and now the learner is trying to do something about this. So formally now the environment is going to change the cost function between rounds in an online learning fashion, and then the learner is going to suffer a loss that has this cost function in its component. And then, of course, the cost function gets revealed to the learner only after it has made its decision. So it is this standard setting, but you have a sequence of states to make things a little more complicated. And then the goal is just to minimize regret. So this is just the gap between the loss of the learner and the best fixed policy in hindsight. Okay, so this has been studied before, by Max. So they had a paper. This is in the transactions and automatic control, where they proposed an algorithm that has a regret guarantee of t to the 3/4, and they pose it as an open problem whether you can improve this to a root t. But if you remember the title of the talk, then you may figure out that we actually improve it by quite a bit to a log square t. Wow. Okay. Apparently the computer couldn't handle this information. What is this? Okay, this is... Oh, it's rebooting or what? Wow. For real, okay.
I won't count this towards your time, so you can say whatever you want.
Oh man, I mean, I had the slide of the century coming up, but that's now ruined by this update. But okay, so what are we gonna do?
We're gonna wait, and you're going to say something. Up to you. No.
All right, man. Okay, so no, I
Tell us more about the log squared.
Okay. So I'm going to tell you. I'm going to tell you without the slides. Okay. So basically, what we have discovered in this work was that Max's paper they missed a convex reformulation of the linearly solvable MDP problem. That gives a very, very easy and very transparent way of analyzing the entire problem. So you can rephrase everything as online convex optimization. And if you look at the structure of the loss, that has actually some very fancy entropy baked into it. It's called it's the conditional entropy of the stationary distributions. So that is a very smooth function. And basically you can just do follow the leader on top of this. And then it is going to give you the fast rate because it's a very smooth loss. Well, because you're lazy. No. Yeah, so it's some technical stuff. We needed to bound some very long sum. We couldn't figure out how to do it, and we just split it in two and log squared. So that's about it, but I want to show you the slide, and then you can clap and all that.
Do you have a lower bound?
No lower bound. We actually don't even know if this loss function that we have is strongly convex or x-concave or anything. It is curvy, but we don't know if it's curvy along the gradient direction. I don't know. This is not funny, I know. Sorry about this. I don't know about jokes. I just...
Can you turn off the lights too?
I can write it here, but... Yeah, I could have brought up my computer.
So, somehow, can you do something related?
Use your own laptop or some other?
Yeah, I was... Can I bring up my own laptop? Is that good? All right, let me just get back to where I was. Okay. Sorry, so the story that we managed to improve this into a log square t, and the reason is that we actually managed to discover that this is a convex optimization problem. So an online convex optimization situation that was not very obvious if you just look at the face of the problem. But what we have discovered is that the whole problem can be... Okay, so part of this is standard. You just reformulated the problem as the learner having to pick stationary distributions. So just imagining that you live in a world where you can select a policy, immediately go to its stationary distribution over the state space, and then just play in this ideal world. And this is going to be this pi t. Okay, and then the laws can be reformulated as something that is linear in the state codes, and it is composed by this R of pi, where R of pi is defined as this. So if you just look at this function, it is still not very obvious that this is a convex function, right? Because this pi log pi component, this is convex, sure, but it is still normalized by pi of y. But so the key insight for us was showing that this is actually a convex function, and it is a nice and smooth convex function. And from this point on, the recipe is sort of standard. So you can just play the follow the leader algorithm. You just look at the sequence of losses in this idealized problem. Good enough. And then you just pick the optimal policy with respect to this. And then, as I established in the beginning, this is, thanks to the linearly solvable property, this can be done by solving an eigenvalue problem. And as for the analysis, yeah, as a result of the smoothness of the loss, we can show that the policies change smoothly as time progresses. So the difference between your consecutive state distributions is going to be bounded by something like 1 over t. And then this immediately leads to a regret bound in the idealized setting of log t. And then the gap between the idealized and the true regret becomes a log square t, which, so there's some technical argument underlying that. And most of the technical tools are taken from Max's paper. We just really reorganized all the lemmas and added the convex interpretation, which revealed the structure in there. Yeah, that's it. Thank you very much for the patience.
We can do one question while Dylan is setting up. Manfred?
Can you somehow move your problem closer or show the relationship to standard hidden Markov model kind of things where you have log loss? What information would you need to make that interesting?
Yeah, so here there's no hidden state. Everything is observable. So I couldn't really make the connection to hidden Markov processes. But I can make the connection to shortest path problems, right? Because those are Markov decision processes, deterministic ones. And if you add dysregularization on top of them, then you can analyze shortest paths in this framework as well, if you like. Okay, that's it. Thanks.